The formal definition of a limit. The goal of this video is to help you understand the formal definition of a limit so that you can then use the definition in epsilon delta proofs.
In this video, I'm assuming that you already have a decent idea of what a limit is.
So here's the formal definition of a limit. Let f be a function defined on an open interval containing c, except possibly at c, and let L be a real number. The statement, the limit as x approaches c of f of x equals L, means that for each epsilon greater than 0, there exists a delta greater than 0, such that if the distance x is from c is less than delta, then the distance the function is from the limit is less than epsilon. Now, looking at the definition, let's note some things. Epsilon and delta are just variables, like x and y. In this case, they represent distances. Delta represents the distances your x values are from c. So then this marks off a region with lower bounds c minus delta and upper bounds c plus delta. And epsilon represents the distance your function values are from the limit. So this marks off a region with upper bounds being the limit plus epsilon and the lower bounds being the limit minus epsilon. Once given an epsilon, we need to show that a delta exists. The easiest way to show anything exists is just to produce one and say, look, there it is. To see how this works, let's look at a very simple example. Let's look at the function x squared divided by x, and let's take the limit as x goes to 0.
So if you're in calculus, you'll probably look at that and say, hey, can't we just cancel one of the x's? And yes, you can.
But there is one exception. X cannot equal 0. So this is the function of f of x equals x, except there's a discontinuity at x equals 0, which makes this a great example. So let's look at the graph. It's just a diagonal line. However, we know there's a tiny hole at x equals 0. That's why we're trying to find the limit there, because we cannot actually evaluate the function there. So we need to look at what's going on really close to x equals 0. In order to do this, we need to zoom in somehow. And that's what the definition allows us to do, but in a well-defined way. So let's zoom in to close to x equals 0. How about let's look at what happens to the function when we are within 0.1 of what we think the limit is. So it really looks like 0 is the limit when you evaluate the limit as x goes to 0. But how can we arbitrarily zoom in and know that things don't go crazy really close to 0? That's where the epsilons and deltas come in. We're choosing an epsilon, and then we come up with a delta that goes along with it. So let's say that epsilon equals 0.1. What x values can we put in the function to get y values that are within 0.1 of the limit 0? So the function is x squared divided by x. It's the same as the function f of x equals x if we're not looking at 0. And the limit only looks at values really close to 0, not 0 itself, so we're okay. So if epsilon is 0.1, then the upper limit for what the function values could be would be the limit plus epsilon, or in our case 0 plus 0.1, or 0.1. And the lower bounds, similarly, is the limit minus epsilon, or in our case 0 minus 0.1, or negative 0.1. Now the x value that corresponds with the positive 0.1 for the function value is also 0.1. And the x value that corresponds to the function being negative 0.1 is also x equals negative 0.1. This would give us a value of delta being the distance our c value is to our x value. So it would be 0.1 in both cases. So we can see that if epsilon is 0.1, then delta is 0.1 as well. Now let's look a little closer up. Say if epsilon equals 0.02. Then the x values of the limit are here and here. And all the x values here would give you function values that fit within epsilon of the limit. So delta is the distance they are from the c value, which is 0 in this case, and delta would also be 0.02. In fact, it will work this way for any epsilon, since f of x just equals x. Our y values are the same as our x values. So when epsilon equals 0.1, delta equals 0.1. If epsilon equals 0.02, delta equals 0.02, etc.
So that means no matter what epsilon you give me, I can find a delta such that if our x values are within delta of our c value, then our function values will be within epsilon of our limit.
Now let's look at another example. So here's another example. Suppose we wanted to prove that the limit as x approaches 5 of 1/5 x minus 2 equals -1. So here's the definition of the limit again. Here's the limit that we're trying to prove. Here's the limits mentioned in the definition. When we look and compare them, we see that c equals 5. The function is 1/5 x minus 2, and the limit is -1. So looking at the function, we can see that it's a line with a slope of 1/5 and a y-intercept of -2. Now, if you've studied limits at all, you know that the limit of a continuous function is just the value of the function at that point. And since f of 5 equals -1, we do know that the value of the limit is also -1. Now, I know you're wondering, why do you have to prove it if it's so obvious? Well, first of all, it's only obvious because someone else proved this property of linear functions before you did. But also, we are trying to train another generation of mathematicians, and in order to prove the hard stuff, you first have to learn the easy stuff. All right, so back to the definition. In order for -1 to be the limit for each epsilon we pick, we must find a delta. So let's pick an epsilon. Let's let epsilon equal 1. Then we need to find a delta. Back to the graph. So if epsilon equals 1, then we're looking at this area around the limit. So since the limit is -1, we're going from -1 plus epsilon to -1 minus epsilon. Epsilon being 1, we get that 0 to -2 is the area we're looking at. So what are the x values that go along with these function values? When the function is -2, it looks like our x value is 0. And when the function value is 0, it looks like our x value is 10. So the x values in between will give us function values between 0 and -2. Now to find our delta. We just see how far these x points are away from our c value, which is 5. And they are 5 units away. So 5 is our delta. Now, delta could have many other values as well. Now remember, we just need to show that a delta exists such that if we are within delta of our c value, the function values will be within epsilon of the limit. So we would just need a delta such that if our x values are within that delta, our function values are within epsilon of the limit. So for example, we could choose delta equals 3. Let me show you that 3 would also work for delta. So if delta were 3, then our x values that are within 3 units of our c value 5 would be between 2 and 8. Then what would our function values be? Well, let's work it out. So we just plug 2 into the function, and the y value would be -1.6. And then do the same over here. We plug 8 into the function, and we get -0.4. All of our function values, since it's a line, would fall between these 2 points. As you can see, this is still within epsilon of our limit, -1. And to show algebraically, we need to show that if the absolute value of x minus 5 is less than 3, then f of x minus -1 is less than 1. So, if delta is 3, then we're going to solve the absolute value of x minus 5 is less than 3. And remembering the rules for absolute value inequalities, yeah, you were wondering when you were going to use that in the future, weren't you? Calculus. So that would mean that x minus 5 is between -3 and +3, And then adding 5 to both sides gives us that x is between 2 and 8, which is what we had before. Then if we take f of 2 minus the limit, -1, that would be -1.6 plus 1, or 0.6, which is indeed less than epsilon, which was 1. The same is true for f of 8. And since we have a linear function, all the values of x between 2 and 8 would give us function values within 0.6 of the limit as well. So it works. Delta could be 3. In fact, delta could equal any number less than 5. But we only need 1 to show that delta exists. Now we know that for epsilon equals 1, we have a delta. Really, that's a pretty wide margin, so it's not really hard to find delta in that case. But the definition says for any positive epsilon, we need to find a delta. So let's try another epsilon. Let's let epsilon equal 0.1. So that gives us a function values of -1.1 and -0.9. So here are the x values that are at -0.9 and -1.1. And so we're looking at this area. So it looks like 4.5 and 5.5 are the x values there. And so each of these are a half of a unit from our c value, which is 5. And so delta equals 0.5. So when x is between 4.5 and 5.5, the function would be between -1.1 and -0.9. So let's check. Let's choose an x between 4.5 and 5.5. How about 4.7? All right, so if we put 4.7 into the function, we get -1.06. So then the distance between -1.06 and -1 is 0.06, which is less than our epsilon, which was 0.1. All right, let's check another one. How about 5.45? So we put that in the function, we take a fifth of it, we subtract 2, we get -0.91. And then we take the difference of that with the limit -1, and we see that that is 0.09, which is less than 0.1, which is epsilon. So let's try another epsilon because the definition says we must find a delta for each epsilon greater than 0. So let's try a smaller epsilon, let's say 0.03. So here we are, zoomed in, and this is how close we have to get to the function. So if we are within 0.03 of our limit, -1, that means we're looking at function values between -1 minus 0.03 and -1 plus 0.03. So if we add 0.03, we get -0.97. And if we subtract 0.03, we get -1.03. All right, there. Then we need to find the x values that go with the function values.
Let's do some algebra. To find what the x values are, we need to set the function equal to the y value and solve for x. So when the function is -0.97, we solve and we get that the x value is 5.15. And then setting the function equal to -1.03, we solve and get that the x value that gives a function value of -1.03 is 4.85.
So how far are these x values away from the c value, which is 5? Well, just do subtraction, you see that it's 0.15. So that is our delta value, 0.15. In order to be within epsilon of our limit, we need to be within 0.15 of our c value. That will give us values of the function between -1.03 and -0.97. So let's check it. Let's pick an x value within 0.15 of our c value. How about 5.1? So we put that into our function, and we get -0.98. If we find the difference between that value and our limit, that needs to be less than 0.03. And it's 0.02, and so we're good. To recap, we chose 3 different epsilon values, and for each one, we found a delta value that works for the function. Can you guess what the pattern is for this function? Here's a clue. Now let's try a different example. So we're going to go through another example of a linear function and its limit. If you feel like you have that down pretty well but want to see a more difficult example, you can just skip to the next example. But let's look at this one. Let's look at the limit as x goes to 0 of 5 minus 3x. So we're going to look at the function 5 minus 3x as x gets really close to 0. So here's our function. It's a line with slope of -3 and y-intercept of 5. So let's zoom in a little to x equals 0. So it looks like the limit is 5, and yes, if we put 0 into the function, then we get that the value of the function at 0 is 5, and since a linear function is continuous, 5 is the limit. All right, so how about let's choose an epsilon, that's 0.3. So if our epsilon is 0.3, the range of values for the function would be 5 minus 0.3, 4.7, and 5 plus 0.3, 5.3. Now, what x values would give us the function value of 4.7 and 5.3? Let's do the math. So, we need to set the function equal to the y value and solve for x. So, we subtract 5 from both sides, and then we divide by -3, and we get that x equals 0.1. If we put 0.1 into the function, we will get 4.7. And now we set it equal to 5.3, and we'll solve that again. Subtract 5, divide by -3, and we get -0.1. So our x values are 0.1 and -0.1. So our delta value would be the distance these numbers are from our c value, which is 0. So if we're given the epsilon is 0.3, then our delta would be 0.1. Meaning, if the distance that our x values are from 0 is less than 0.1, then the distance our function values are from 5 will be less than 0.3. So whenever we are within 0.1 units of our c value, 0, we will be within 0.3 units of our limit, 5. Let's check it out. Let's pick a value within 0.1 of 0. What about x equals -0.05? So if we put that into the function, we would then multiply by 3, take 5 minus that, and we get 5.15. Now the difference between the function value and the limit needs to be less than epsilon. So we found f of -0.05, which is 5.15, and the limit is 5, so the difference is 0.15, which is less than 0.3. All right, let's look at a different epsilon, even closer. Let's let epsilon equal 0.06. So we're looking at values between the limit minus epsilon and the limit plus epsilon. In this case, it would be 5 plus 0.06 and 5 minus 0.06. And so it's between 5.06 and 4.94. Okay, so what x values are we looking at here? Let's do the math. So we set the function equal to the y value and solve for x. Subtract 5 from both sides, then divide by -3. And we get x equals 0.02. And now we'll set it equal to 5.06 and solve again. Subtract 5 from both sides, divide by -3, we get that x equals -0.02. So our x values are -0.02 and +0.02. So to find our delta, we take the difference in our x value and the c value. So delta equals the absolute value of 0.02 minus 0, and we get that delta equals 0.02. That means that any x value within delta, which is 0.02 of our c value, we give a function value within epsilon, which is 0.06 of our limit, which is 5. So let's check something really close to the edge. Let's try x equals 0.019. Just put 0.019 into the function, multiply by 3, take that from 5, and we get 4.943. So the function value at 0.019, just within our delta, is 4.943. So the function value was 4.943, subtract the limit, which is 5, and we get that that's 0.057, which is less than 0.06. So we're good. So when x equals 0.019, f of x equals 4.943, and is within epsilon of our limit 5.
Now, it's important to note that we'd have to check every single value in this interval in order to prove that this delta works. And obviously, since there are infinitely many values, that's impossible. So for the proof, we're going to have to use algebra. But for now, checking one helps illustrate the principle of the epsilon delta definition, and if when we checked it, it wasn't right, then we'd know that we did something wrong.
So for our function, we chose epsilon equals 0.3 and we found a delta, which is 0.1, meaning that whenever our x values are close enough to 0, within 0.1 of our c value, or 0, then all the function values will be within 0.3 of 5, which was our limit. And when we chose epsilon equals 0.06, then we found a delta, which is 0.02, so that if all of our x values are close enough to 0, within 0.02 of 0, then all our function values will be within 0.06 of our limit, which is 5. Let's do one more example that's not a linear function. So here, our final example is neither linear, nor can we find the limit just by plugging in the c value. Let's look at the limit as x goes to 1 of x to the third minus 1 divided by x minus 1. So here's the pretty little graph of our function. And as you can see, if we plug 1 into the equation, we get that the denominator equals 0, and yeah, so let's not do that. So since we can't evaluate the function, what we can do is look at the graph and see that it looks like the limit is 3. Let's zoom in a little more. By the way, there is a point of discontinuity here, since the denominator cannot equal 0. But it does look like the limit is 3. So, reviewing again the definition of the limit, let's see how it compares to our specific example. We would see that the c is 1, that the function is x to the third minus 1 over x minus 1, and the limit is 3, probably. So let's try some values for epsilon. Let's try 0.5. Then our boundaries are plus and minus 0.5, giving us function values between 2.5 and 3.5. Now let's figure out the x values that go along with this. So let's set the function equal to 2.5 and to 3.5 and solve. Now to solve this, it's a little complicated, hence our choice of linear functions before. And you need to remember that you can factor the difference of cubes. Now, I had to look this up because although I've taught algebra a lot of times, it's been a while and I didn't remember. However, isn't the internet a wonderful thing? Back in the day, I would have had to come up with a copy of an algebra book or do some fun math on my own to figure it out. Anyway, this factors as such. So we can cancel the x minus 1s as long as x minus 1 doesn't equal 0, as long as x doesn't equal 1. But it's okay. We're looking at values really close to 1. We're not actually looking at the value of the function at 1 itself. That's why we're taking a limit. So if we cancel, we get this quadratic equation. Remember how to solve quadratic equations? We have to use the quadratic formula. And here it is in case you forgot. Notice, the expression that we have must be equal to 0. So we're going to subtract 2.5 from each side so it gets equal to 0. And then, using the formula, we get that x equals -1 plus or minus the square root of 7, all divided by 2. And the plus and minus give us two different values, positive 0.823 and negative 1.823. So there's one, and there's another. All right, now since we're just looking at the values close to 1, we can just look at the positive value. All right, let's solve for 3.5. So we set the function equal to 3.5. Remember, that's the higher boundary. And we can cancel the same way because we're not looking right at 1. We need to subtract 3.5 from both sides to get it equal to 0. We need to stick it into the quadratic formula. And we get that x equals -1 plus or minus the square root of 11, all divided by 2. Gives us two values, one for the plus, one for the minus, and those values are 1.158 and -2.158. And here they are. And again, we only need to look at the one that's close to 1, because that's where we're taking the limit. All right, now remember our goal is to find delta. We had that epsilon, now we want to find the delta that goes along with it, so that all the x values within that delta will give us a function value within our epsilon. So, looking at our values of x, how far away is each x from our c value? One of them is 0.177 away, and the other one is 0.158 away. So, which one is delta? Well, if we have to guarantee that all the function values within delta must be within 0.5 of our limit 3, then we need to take the smallest value. And so delta would equal 0.158. Or delta could equal anything smaller than that as well. All right, so we're just going to show you. If we use the smaller value, then we see that the function values are not more than epsilon away from the limit 3. But if we use a larger value, we're okay on this side. But on this side, we are not within epsilon of 3. So we can't use delta equals 0.177. We have to use the smaller value, which is 0.158. Let's pick one more smaller epsilon. How about 0.06? So going back to the function, let's zoom in again, very close to 3. And it looks like these are the function values that would be within 0.06 of 3, which is our limit. And what are these x values? So if we let epsilon equal 0.06, we want to take the limit plus and minus 0.06, and that would give us that the values of the function are between 2.94 and 3.06. Now, what are the x values that go along with that? Yay, algebra, here we go again. So we are going to factor, we're going to cancel, we're going to set it equal to 2.94. We will then subtract 2.94 to get it equal to 0 so that we can stick it into that quadratic formula. And a little complicated, but we get two values, 0.980, -1.980. And we need only the part that's close to 1, so we're going to go with the positive 0.980. Now we do the upper limit, set the function equal to it, solve for x by using the lovely quadratic formula, and we get 1.02 and -2.02. All right, here are x values. They are around 1, 0.980 and 1.02. And you can see they align to the box we drew, showing the function values that we need to be within. So that shows if our x values are between 0.98 and 1.02, the function values will be within 0.06 of the limit, which is 3. Now, since we're dealing with a smaller window and we rounded to 3 decimal points, you can't tell that the x values are not the same distance from 1 this time, though they aren't exactly the same distance if you would round out to more decimal places. But since we have to round somewhere, square roots are not rational, we'll just go with this. So our delta is 1.02 minus 1, or 1 minus 0.980, and that would be 0.02. So delta exists. We needed to show that a delta exists, and there it is. So in summary, we found that when epsilon is 0.5, delta is 0.158. We found that when epsilon is 0.06, delta is 0.02. But remember, for the limit to be proven, we must provide a delta for each epsilon. How do you do this, you say? Well, look at my video that talks about proofs. It's going to involve some algebra. But hopefully, in this video, you get the idea of how the epsilon delta definition works, at least when you have a set value for epsilon. Keep your eye out for the video about epsilon delta proofs.